Hello everyone, welcome to the next lecture of bipolar junction transistors, chapter number 6 of the book. This is our last lecture on chapter number 6, bipolar junction transistors, and in the next lecture we are going to move towards amplifiers, the topics related to the BJT in chapter number 7. Okay. So in the last lecture, we did some of these example problems where we used the NPN BJTs in different DC circuit applications. We solved different circuits. We find out different node voltages and the current values. So today we are going to start from there. We will do one more example, and then we will cover some of the leftover topics in today's lecture. Okay. So let's do one more example. Okay, so we have the circuit over here, and again we want to analyze the circuit and determine the node voltages and the branch currents. Okay. Now, if we look at the circuit, we kind of solved a portion of the circuit already in the last lecture, and I am more precisely talking about this portion of the circuit. We saw that, for example, the values, you can compare the values RB1 100K, RB2 50K, RC1 5K, RE3K, NPN transistor, and a 15 volt biasing power supply. So let me go back. On this example, you will see that this circuit is exactly similar to what we are seeing right now on the in the example on the left side. Our Q1. So we have a Q1 transistor. So this was our Q1 transistor in the current example, and our voltage values are the same. Our resistors are the same. So while solving this problem, the first thing that we did is we created this Thevenin equivalent, and we find out this value of the VBB. We find out the value of RBB. So once we find out these values, then we calculated the values of emitter current, base voltage, collector current, collector voltage. Where is the base current value? Here's the base current value. Okay. So we did, since all the values of the resistors are the same and our transistor is the same, our biasing voltage is the same, so we are going to probably use the same number. So let's go back to our current problem. Okay, so we want to solve this circuit. So the only difference with the previous example and this example, what we have is, now we have another transistor Q2, which is a PNP transistor, and that is connected to our Q1 transistor, which is an NPN transistor. Okay, so this is the only difference, that we have this Q2 that is connected to this Q1 with the base circuit. Another difference that we have is, now we have this IB2 current that is flowing as well. Right? So what this will do is, initially, assuming that when we do not have a Q2, the current that is flowing from IRC1 should be equal to IC1, considering IB2 equals 0, right? So for example, if there is no current, if I don't assume these two transistors to be connected, this means that our IRC1 and IC1 will be equals to 0, and we have the circuit, right? So, okay. So before solving this circuit, so the first thing that we will do now is, I am going to assume that the value of the IB2 is very small as a first approximation, and I will write down all the voltage values and the current values for this circuit that we have already solved. Okay, so the values are over here. So over here, my values of, so these are the Thevenin equivalents. I think these are the final values. The emitter current is 1.29 milliamperes. Collector current is 1.28 milliamperes. All right. So our emitter current, IE1, was 1.29 milliamperes, right? So this is our IE1 now. IE1, and then we have our collector current IC1. So this was IC1. Again, assuming IB2, or kind of neglecting the IB2, or considering IB2 to be very, very small to be neglected, I can write this over here. IB2 neglected. If we neglect the IB2, then our currents will be the same as we solved in the last circuit. Our IE1 will be 1.29 milliamperes. IC1 will be 1.2 milliamperes. The voltage at the base terminal will be, what was the voltage at the base terminal? 4.57. The voltage at the base terminal will be 4.57 volts, right? So this is the voltage at the base, VB1. And then what is the value of the base current? IB1. The value of the base current will be equals to, where is the base current? 0.018, 0.0128 milliamperes. 0.0128 milliamperes. All right. Now, so we ended up writing down these values from the last example. So interestingly, the one thing that we can see is our collector voltage, right? Even considering IB2, not to be neglected, our collector voltage can be different. So our VC1 can be different and depends on IB2, right? Okay. However, as first approximation, we can assume IB2 to be neglected, right? When we neglect the IB2, then our VC1 will be, we are going to find out our VC1 value is essentially the same as what we solved in the last circuit. So our VC1 value, and this neglecting the IB2 means our IRC1 equals to IC1. Otherwise, they will not. Because we're going to have a different IRC1 that is flowing, and we have some small value of the IB2 that is flowing as well. Okay, so considering again IB2 to be neglected, our value of the VC1 would be equal to, we can solve this thing, 15 volts minus IC1 RC1. So 15 minus IC1 is 1.28 milliamperes. And what is RC1? 5 kilo ohms. The value that will come out to be 8.6 volts. And this value is the same as what we computed last time too for the collector voltage. This is the last example, right? So this was the collector voltage, 8.6 volt. Right, we got the same value again because we neglected the IB2. And if you neglect the IB2, this means that your left part of the circuit, Q1 circuit, is essentially the same as we did in the last example. All right. So I ended up writing down all these values because we solved the last example earlier in the last lecture. However, if this problem is presented to you as is, then you essentially have to solve initially this left portion of the circuit, Q1, and then do the Q2 part. Okay. So as a first approximation, again, we neglected the current IB2. This means that our IRC1 current that is flowing in this branch is the same as this IC1 current that is flowing over here. Right, so this is VC1. So this current and IRC1 is the same, neglecting IB2. So we ended up finding the value of the VC1. Again, again, we can see that our VC1, which is 8.6 volts, is greater than VB, which is, what's the base voltage? VB1, 4.57, right? So our Q1 transistor is in active mode of operation. All right. All right, so this is good. So the next thing that we need to do now is let's find out the voltages of the, let's find out, considering still IB2 to be smaller, let's find out the node voltages and the node currents of the transistor Q2. So now again, please note that our transistor Q2 is a PNP transistor, right? So it's a PNP transistor. And our collector voltage is here. Our emitter voltage should be here. And our base voltage should be here, VB2. Okay. So now let's find the emitter voltage, VE2. So the one thing that we can notice over here is that since our IB2 is neglected, our VC1 and VB2 will be the same, right? Q2, IB2 neglected. So our VC1 should be equals to VB2, the base voltage values, right? So the voltage values at this potential, at the base of the Q2 and at the collector terminal of the Q1 should be the same. Okay, now let's find the emitter voltage. Now we need to find the emitter voltage, VE2. So this can be found out by, so let's do this thing. We know that VEB2 should also be equals to 0.7 volts, which should be VE2 minus VB2. I know the value of VB2, so it should be again 0.7 plus VB2 equals VE2. So VE2 equals 0.7 plus VB2. VB2, we just saw that VB2 value is equals to VC1. So 0.7 plus VC1 equals 0.7 plus, what is the value of the VC1? This is the value of the VC1, 8.6 volts. 8.6 volts, so it will come out to be 9.3 volts. So the value of VE2 is 9.3 volts. All right, so we ended up finding the value of VE2, which comes out to be 9.3 volts. So the next thing that we need to do, we need to find out the value of IE2. And IE2 can be easily be found by multiplying VE2. No, we have a biasing potential here as well. Right, so we can easily solve the circuit. 15 minus, in order to find IE2, 15 minus VE2 divided by RE2 should be IE2. All right, so next find IE2 can be found out by biasing potential minus VE2 over RE2. So it should be 15 volts minus VE2 voltage, 9.3 volts divided by RE2, 2 kilo ohms. So once you solve this equation, 15 minus 9.3 over 2, the answer you will get is 2.85 milliamperes. So the value of IE2 will be 2.85 milliamperes. Okay. So we ended up finding the value of IE2 as well. Now let's find out the value of IC2 and VC2. And we in all the previous examples, we see that before finding the value of the collector current, what we need to do is we need to figure out whether our transistor is in the active region or the saturation region. So we make an assumption and then validate that assumption. Okay, so we are going to make an assumption now. Assume Q2 in active region. And then we can always start from the active region, and if this doesn't work out, then we can move to the saturation region. All right. So assuming Q2 to be in the active region, we can start with, let's find the collector current. So IC2 can be, so we know that collector current is equals to alpha times IE. So IC2 can be alpha times IE2. Our alpha, it was not given in this question since our circuit was the same. And let's see if it's given in the previous example. So in the previous example, the beta was 100. Okay, so we can use the same value of the beta here. It was not provided, so you can assume the beta value to be 100. All right. Okay, so I'm going to assume beta to be 100. All right, so once we assume beta value to be 100, alpha equals to beta over beta plus 1, 100 over 101, which comes out to be 0.99 approximately. All right, so what you get is 0.99 multiplied by IE2, 2.85 milliamperes. The answer for IC2 will be equals to 2.82 milliamperes. So this is the value of the collector current. We ended up finding the value of the collector current. The next volt value that we need to find is the VC2. VC2 is simple, IC2 multiplied by RC2. Right, so our VC2 is IC2 into RC2. So our IC2 is 2.82 milliamperes. RC2 is 2.7 kilo ohms. So the value of the VC2 that we will get, if you multiply 2.82 with 2.7, will be so VC2 will be equals to 7.62 volts. All right. So we ended up finding the value of that collector voltage for the transistor 2. Now, again, we need to after finding the collector current, the collector voltage, we need to verify our assumption whether the transistor is actually in the active region or not. So our VC2 is 7.62 volts. And what is our base voltage? Our base voltage is VB. Going back here, we assume the VB to be 4.57, again neglecting IB2 to be being neglected. Okay, so 4.57. So our collector voltage is at a higher potential as compared to the base voltage. Okay, so yes, okay, so our base voltage is 4.57 and the collector voltage is this. Since our collector voltage is at a higher potential as compared to the base voltage, so this means that our Q2 is still in the active region. Q2 is in active region. Again, let me cross-check this. Our collector voltage is 7.62 volts here, and our base voltage is 4.57, right? So our collector voltage is at a higher potential as compared to the base voltage. So our Q2 is in the active region. All right. So once we do that, while doing all of this analysis, the one thing that we have assumed till now is that our IB2 current is neglected, right? Now what we are going to do is we are going to find out the value of IB2, and then we have to reevaluate all of these values again in this iterative process. Okay, so now we are going to calculate value of IB2. Okay, so in order to calculate the value of IB2, we can use this equation, IB equals, and we have seen this equation before, beta plus 1. So again, IB2 equals to IE2 over beta 2 plus 1. Again, we are assuming beta 1 and beta 2 both are assuming to be 100. So the value of IE2 from the last is 2.85 milliamperes. So you have 2.85 milliamperes divided by 101. The answer comes out to be 0.028 milliamperes. Right, so this is the value of IB2 that we got, 0.028 milliamperes. And notice that this value is very small as compared to the value of the collector current, 1.28, or that was flowing. So that is why neglecting it was a fair assumption, but now we needed to see whether our assumption, the differences that our assumption made, how far those differences are, and we need to do this iterative calculations to minimize this error. Okay, so this is our new value of IB2. Once we find out the new value of IB2, right, so if we have a new value of IB2 and now we are not neglecting this value, this means that our IRC1 and IC1 are not equal, right? So with this thing in mind, our IRC1 is not equal to IC1. So with this in mind again, our IC1, going back to the circuit again, right? So our IC1 should be a summation of IRC1 plus IB2. Our IC1 should be a summation of IRC1 plus IB2. So I'm interested in finding the value of IRC1, which should be equals to IC1 minus IB2. What is the value of IC1? IC1 is 1.28 milliamperes. 1.28 milliamperes minus IB2. The new value of the IB2 is 0.028 milliamperes. So the value of IRC1 that we will get is 1.252 milliamperes. So this is the value of IRC1 that we got, right? Since we have a different current that is flowing through this RC1 resistor, this means that my collector voltage for the transistor Q1 will also change. Now let's find out the value of the collector voltage, VC1. So VC1, again, VC1 can be simply be figured out by using the circuit 15 minus IRC1, RC1 current, right? So this should be 15 volts minus I RC1 into RC1. So this should come out to be 15 volts minus IRC1 is 1.252. 1.252 milli into RC1 is 5 kilo ohms. 5 kilo ohms. So the answer for the VC1 that will come out to be 8.74 volts. Okay, so this is the new value of VC1, right? So this is the new value of VC1 that we got. Okay, great. So once we find out the value of the VC1, essentially we have to repeat the same process that we did before to find out all the rest of the values. Once we have the new value of the VC1, we need to find the new values of VE2, right? So our VE2 is VC1 plus 0.7, right? So our VE2 is, what was it? 0.7, which was VEB2 plus VC1. VEB2 plus VC1, 0.7 plus 8.74. So the emitter voltage value will come out to be 9.44 volts. This is the new value of the emitter voltage. So after finding the emitter voltage, we ended up finding the emitter current. And the emitter current was, again, the emitter current is flowing over here. We have a new emitter. Sorry, this is the emitter. So we ended up finding the emitter voltage over here. So the new value of the emitter current will be 15 minus VE2, the new value of VE2 divided by RE2. So the new value of IE2 will be equals to 15 volts minus VE2 over RE2. So 15 minus VE2 is, what is the value of VE2? 9.44 divided by RE2. The value of the RE2 is 2 kilo ohms. So the value that we got for the emitter current IE2 will be 2.78 milliamperes. So this is the new value of the IE2. Let's see what we did after that. After that, we ended up assuming the transistor operation in the active region, and we ended up finding the collector current, IC2. So the IC2 can be found by alpha times IE2. Our value of the alpha will remain the same, 0.99. So let's find the value of IC2. IC2 equals alpha times IE2. Alpha is 0.99 multiplied by 2.78 milliamperes. This will come out to be 2.75 milliamperes. This is the new value of the collector current. After collector current, we find the collector voltage, which was IC2 RC2. You can also look it from here. So after finding out the collector current, we can easily find the collector voltage by multiplying IC2 with RC2. So our new value of the collector voltage is, we have IC2 into RC2. So this is 2.75 milliamperes into 2.7 kilo ohms. 2.7 kilo ohms. This will come out to be 7.43 volts. Okay, so again we ended up finding out the new value of collector current. Now we can also find out, so let's see what is the new value of the IB2. So we ended up finding out all the voltage values, right, which was our main goal. So first we assume, so by now what we have done is we started with the circuit, and assuming that you haven't done the previous problem, first you need to solve this portion, right? find the Thevenin equivalent, and find out all the node voltages, assuming neglecting the IB2. So once we do that, we've ended up finding out all the values of emitter current, collector current, base voltage, base current, and we assume the IB2 to be neglected. This means that our IRC1 and IC1 was same, and our collector voltage was the same as the base voltage for the second transistor. Then we ended up solving the second transistor, where we first find out the emitter voltage. Again, our VEB2 to forward bias the PN junction should be 0.7 volts, and we just reverse the polarity of the battery for a PNP transistor. So once we find out the emitter voltage over here, we can simply solve the circuit by 15 minus VE2 over RE2 to find IE2. So this is how we ended up, where did it go? Okay, yeah. So this is how we ended up finding the IE2 value. After finding the IE2, we made an assumption of the transistor Q2 to be in the active region, find the value of IC2 and VC2. Okay, so once we find all the values, then we said that, okay, so let's see, so all of these values should have some error because we neglected the base current. So in the second iteration of solving this circuit, what we did is we find out what is the value of the base current. What is a good approximation of the base current? So we made an approximation of the base current using this equation, and we find out this value of the base current. So our base current was 0.028 milliamperes. So we got a new value of the base current. So once we got our value of the base current, this means that our current flowing through RC1 should not be equal to IC1 because we have a base current flowing. This means that we need to find a new value of the collector voltage. So this is what we ended up doing. We ended up finding a new value of the collector voltage. Before doing that, we had to find the current that is flowing through the RC1 resistor. Okay, so then we repeated the same process. We found the collector voltage value, then the emitter voltage value, emitter current, collector current, and then we find the collector voltage value for the second transistor. So once we did all that, let's find out again the base current and see whether that base current will matches with our previous iteration or not. So what we do is, we know that we are going to use the same equation. Now let's find the base current again. Now let's do second iteration. Second or third iteration, I guess this time. So our new value of IB2 equals our new value of IE2 over beta plus 1. IE2 was 2.78 milliamperes, 2.78 divided by 101. When we calculated this value now, our value came out to be 0.0275 milliamperes. If I compare this value with the earlier value of the base current that I got, the values are pretty similar, right? 0.028 and 0.0275 milliamperes. The values were very similar, and there was not a huge difference in the base current, so I can fairly stop my iterative analysis over here and say that these are the node voltages and the currents that we obtained. Otherwise, we can now, using this equation, if we wanted to do another complete iteration, now we could have used this base current and then restarted this entire procedure over here with a new value of the base current. So we can do this iterative analysis in the loop to converge and to minimize the error and to find the exact values of these node voltages and the currents. All right, so with that, this was our final example of this chapter that we wanted to do. Now I want to discuss a couple of very quick concepts before wrapping up our lecture. Okay, so transistor breakdown. So by now, we have discussed that we have a bipolar junction transistor, NPN or PNP. It has two junctions, the emitter-based junction, collector-based junction. Right, so the maximum voltage, and this is what you have discussed as well, but you have studied as well in the PN junction diodes chapter, right? So the PN junction has this maximum voltages that we can apply before the junction will break down or it will enter into the avalanche region. And what happens in the avalanche region? We have a huge amount of current that will flow through it. And unless and we can kind of if we can kind of dissipate that current, we can preserve the transistor and no permanent damage usually happens. Okay. So similarly, for both of these junctions, emitter-based junction and collector-based junction, there are breakdown voltages at which the transistor or those junctions enters into the avalanche. And a huge amount of the collector current will start to flow. Okay. So let's see. So this is our common base characteristics. We have a collector current and we have a collector to base voltage over here. And you can draw these characters using the circuit, right? So for a fixed value of the emitter current, you can vary the value of the collector to base voltage, find out the value of the collector current, so you can draw these characteristics, right? So you can develop all of these characteristics here. Now, however, what happens that at a specific voltage value, at a specific voltage breakdown voltage value, we are entering into this avalanche mode or avalanche region. Okay, so again, this is a common base configuration. So let's look at this first line over here. So at this line, we have emitter current equals 0. So emitter current equals 0 means that our emitter is open circuited. So the breakdown voltage or the voltage at which our collector to base junction will break down when the emitter is open circuited is denoted by this BV breakdown voltage for the collector to base junction when the emitter is open circuited, right? And at this voltage, we have this huge avalanche multiplication or a huge flow of the current, right? So when the emitter is open circuited, the collector to base junction breaks down at this value BV CBO. And another thing that you can realize that for a higher values of emitter currents, when you do not have an open circuited emitter terminal, however, you have an emitter current flowing, when that is true, the breakdown voltage reduces or the breakdown voltage reduces with the increase in the emitter current that is flowing through it. Right, which we can see with a slight decrease in the required breakdown voltage values as the emitter current is increasing. The typical values of this breakdown voltage for the collector to base junction with the emitter open circuited, this value is approximately greater than 50 volts. And this is what we just discussed. For when emitter current is greater than 0, the breakdown voltage occurs at a smaller voltage values than the CBO. Right, so it occurs at a smaller voltage values, and with a further increase, there's a slight decrease, there's a slight continuous decrease in the breakdown voltages. Okay, so now let's look at so right now we just discussed the common base configuration. Now we are going to quickly talk about the common emitter configuration, right? So okay, so this is a common emitter characteristics you have seen it multiple times by now. We have a collector current, we have a common collector to emitter voltage that is applied. Again, you can keep the base current constant or a fixed value and then change the values of the collector to emitter voltage, find out the values of collector current, and you can draw these statistics. This is again the separation in between the saturation and the active region. We discussed this thing. This is approximately VCE saturated value, if you remember. This is approximately 0.3 volts. All right. So let's discuss this characteristics, common emitter breakdown characteristics. So when we have our open base, our base current is equals to 0. The voltage value at which our collector to base junction will break down is written as BVCEO. The value of this BVCEO compared to BVCBO is usually smaller, right? So this value is greater than the value of the common emitter breakdown voltages values, and it is almost half to the to this value of breakdown voltage of CBO. This value, BVCEO, is also referred to as a sustaining voltage and also denoted by this LVCEO in certain data sheets. Again, another important concept that I just talked about in the last slide as well. our collector to base junction either in the common emitter or the common base configurations, right? Once it enters into this avalanche mode, a large amount of this current flows. However, if we have a dissipation circuit there, then our transistor will not permanently damage. However, without any dissipation of this current, the transistor can permanently damage. All right. So by now we have talked about the common collector base junction breakdown voltages. Very quickly, how does that compare with the emitter base junction? Our emitter base junction usually breaks down at much more smaller voltage values as compared to the collector to base junction, right? So the breakdown voltage values for the emitter to base junction is around 6.6 to 8 volts, and they are more destructive in a sense that at those breakdown voltage values, the beta value of the transistor gets permanently reduced. And once this happens, even if your BJT can be operational, but the beta values cannot be relied on, and those values have been reduced, so you cannot kind of use it the same way or with the same design considerations. One last thing that we talked about, that yeah, it's so we said that we discussed different beta factors, the common emitter current gain beta. So we discussed that this thing is a constant for a given transistor, it's a transistor parameter. We also, by the way, saw that in the saturation mode we have a forced beta. Just to say it again, and what usually happens is our base current is increasing and our collector current decreases when our transistor moves from the active region to the saturation region. So in the saturation region, our beta value reduces. All right. So anyways, for a specific transistor, since it's a transistor parameter, so we have a constant value for a given transistor, this common emitter DC current gain. All right. So this statement is not entirely true as well, because this value, the value of this DC current gain beta, it also depends on two parameters. It depends on the temperature at which we are operating the transistor, and it also depends on the value of the current. More precisely, collector current, IC. All right. Here's the plot, right? So on the y-axis we have beta, on the x-axis we have collector current. So let's look both of them. The first thing is the temperature. You can see that the beta value is increasing, right? Beta value is directly proportional with the temperature. As temperature increases, the beta value increases. The second important thing that we can see over here is that our beta value does not necessarily increase or decrease for the collector current. It follows this unique characteristics, right? So based on these characteristics, we can pick a collector current at which we have a specific, or we get the maximum value of this common emitter current gain. Right, so one problem that we can face is while operating the transistor at higher temperatures is the beta value increases, right? So we want to make sure that our we know at which temperatures, at which power levels we are operating the transistor, and what is the value of the collector current and what is the value of the beta in terms of design consideration and design analysis. So with that, so this was the final topic of our chapter number 6. With that, we are kind of ending our chapter number 6 is ended now. And in the next lecture, we are going to start with chapter number 7. And we already covered the contents of chapter number 7 related to MOS FETs. However, now in the next lecture, starting the next lecture, we are going to cover the contents that are related to BJT amplifiers. So we have one more week left in which we are going to discuss in more details on the BJT amplifiers. So with that, thank you so much, and have a good rest of the day or night whenever you are watching this lecture. Thank you. Bye-bye.